The topic is Introduction to Fractions and Mixed Numbers. The objectives in this topic: identify the numerator and denominator of a fraction. Write a fraction to represent parts of figures or real-life data. Graph fractions on a number line. Review division properties of 0 and 1. Write mixed numbers as improper fractions. Write improper fractions as mixed numbers or whole numbers. So in a fraction, the top number is called the numerator, and the bottom number is called the denominator. The bar between the numbers is called the fraction bar. So if we have the fraction 5/6, that's a numerator of 5, a denominator of 6. The numerator is the number of parts being considered, and the denominator is the number of equal parts in the whole. So a fraction 5/6 or 5/6 represents 5 out of 6 total parts. And those total parts are equal parts. So let's identify the numerator and denominator of each of these fractions. 11/2, the top number is the numerator, the bottom number is the denominator. So 11 is numerator, 2 is denominator. 10y/17, top is numerator, bottom is denominator. So 10y is numerator, 17 is denominator. Let's write a fraction to represent the shaded part of the figure. First of all, how many equal parts are there total? 1, 2, 3, 4, 5, 6, 7. So this would be sevenths, a fraction over 7. How many of these parts are shaded? 1, 2, 3, 4. So in the figure, 4 out of the 7 equal parts are shaded. Thus, the fraction is 4/7. A more real-life example: write a fraction to represent the shaded part of the diagram. This is medical. We have a syringe. The liquid holding space is divided into 10 equal parts. The liquid in the syringe is 3 of those equal parts. So 3 out of the 10 total capacity parts are being used. So 3 out of 10 is the fraction 3/10. Let's go the other direction. Let's draw a figure and then shade a part of it to represent the fraction 5/6. Since the denominator is 6, we're going to divide the rectangle into 6 equal parts. And we chose a rectangle because that's going to be the easiest to divide up equally. Then we shade 5 of the equal parts. So draw a rectangle, split it up so that there's 6 equal parts. That would be 5 dividing lines. Shade 5 of those parts, and then 5/6 of the rectangle is shaded. We've represented 5/6. Up until now, we've been looking at what's known as a proper fraction. And a proper fraction is a fraction whose numerator is less than its denominator. So the number on top has been smaller, like 3/8. An improper fraction, on the other hand, is a fraction whose numerator is greater than or equal to its denominator. So a proper fraction, the top is strictly less than the bottom. An improper fraction is anything else. If the top and the bottom are equal, or if the top is greater than the bottom, we have an improper fraction. For instance, if we have 3 triangles, each divided into 4 equal pieces that are also triangles, you'd have to imagine that this bar that goes across this triangle here is also here and here. That looks like a bit of a mistake. But each of these three triangles is separated into 4 equal smaller triangles. And 2 of them are shaded completely, for 4 and 4 makes 8 shaded pieces. The third has 2 out of the 4 shaded. So adding those 2 to the other 8, that's 10 shaded pieces. But we're divided into fourths. So this represents 10 fourths, or 2 wholes and 2 fourths. So 10 fourths is equal to 2 and 2 fourths. Another way to visualize fractions is to graph them on a number line. Between 0 and 1, if we draw 4 dividing lines, splitting the space between 0 and 1 into 5 equal parts, then each of those equal parts would represent 1/5. And 3 of those 1/5s together would represent 3/5. So as we go from 0 to 1, our notches would be 1/5, 2/5, 3/5, 4/5, and then 5/5. And 5/5 equals 1 because 5 divided by 5 is 1. A fraction is just a division problem. Likewise, on the left end, 0/5 equals 0 because 0 divided by 5 is 0. So let's graph the proper fraction 3/4 on a number line. We're going to divide the distance from 0 to 1 into 4 parts. That's 3 dividing lines to get 4 equal parts. Halfway between 0 and 1 is 1/2. But if we count off our fourths, we have 1/4, 2/4, 3/4, 4/4. We've already discussed that 4 over 4 is 1. 4 divided by 4 is 1. So that's why our number over itself happens at 1. We've already discussed that 0 over our number is 0. So that's why 0 is 0. But it looks like 2/4 is also equal to 1/2. 2 out of 4 represents half of the figure. But this isn't about 2/4 or 1/2. This is about 3/4. And to graph that on the number line, we divide our distance like so, and then place a point. 3 of those marks over. 1, 2, 3/4. Let's use the number line method to graph the improper fraction 8/3. We would divide everything up into thirds and then count 8 of them over. 3/3 takes us to 1. But we want 8. So 4, 5, 6, 7, 8. 8/3 is all the way over here. Since there was a bit of reducing going on with 3/3 and 0/3, even 6/3 and 9/3, since fractions are division problems, let's review our special division properties of 0 and 1. If n is any integer other than 0, because we can't have 0 on the bottom, we can't divide by 0, n over n, or any number over itself, equals 1. We've seen that already in this topic. We've also seen that 0 over any number is 0. We also have that any number over 1 is itself, and any number over 0 is undefined. So 9 over 9, a number over itself, is equal to 1. -6 over -6, a number over itself, is equal to 1. Negative over negative is positive. So even with a negative number over itself, we get +1. 0 over -1. 0 over any number is 0. 5 over 1. Any number divided by 1 is itself, so 5. 13 divided by 0, we can't divide by 0. We can't have 0 on the bottom. That's undefined. And -13 over 1. Any number over 1 is itself, -13. Earlier, we saw what is a mixed number, a number with a fraction attached to it, and we saw that it was equal to an improper fraction. Rather than drawing it out every time, we have this method of writing a mixed number as an improper fraction. Multiply the denominator by the whole number, whoops, and then add the numerator to that product that we get. Take that result and write it over the original denominator. So A and B here are two examples of mixed numbers, a whole number part and a fraction part. We want to write each as an improper fraction. We start at the bottom, multiply, and then add. We're going up and around, starting with the 7 times 5 plus 2. 7 times 5 is 35, plus 2 is 37. And we keep that over the original denominator of 7. 5 and 2/7 is 37/7. In B, start at the bottom. Start with the 5. 5 times 4 plus 1. Keep that all over the original denominator of 5. 5 times 4 is 20. 20 plus 1 is 21. So we get 21/5. So that's a nice little method we have to go from mixed number to improper fraction. Now, to go from improper fraction to mixed number or improper fraction to a whole number, we're going to divide. Top divided by bottom. Divide the denominator into the numerator. Numerator divided by a denominator. The whole number part of the mixed number is the quotient. And then the fraction part of the mixed number is the remainder over the denominator. So we've looked at division problems before that have had remainders. For instance, if we had 9 divided by 5 before, we would say that 5 goes into 9 once and there was a remainder of 4. Five goes into 9 once. 1 times 5 is 5. 9 minus 5 is 4. We would say 1 remainder 4. But now that we know fractions, instead of saying 1 remainder 4, we take that remainder of 4 and we put it over the denominator of 5. We would say 1 4/5. Likewise, B, 23 over 9. Set up long division. 9 goes into 23 twice. 2 times 9 is 18. Subtract. 23 minus 18 is 5. Instead of saying 2 remainder 5, we say 2 5/9. Put that remainder over the original denominator. And that's it for this topic. The topic is factors and simplest form. The objectives in this topic are write a number as a product of prime numbers, write a fraction in simplest form, determine whether two fractions are equivalent, solve applications by writing fractions in simplest form. So to perform many operations, it is necessary to be able to factor a number. This is why I said that our multiplication tables are important. Having those multiplication facts memorized is important. For instance, since 7 times 9 is 63, 7 and 9 are factors of 63. 7 times 9 is called a factorization of 63. We need to be able to see 63 and immediately think 7 times 9. Numbers can be classified as either prime or composite. A prime number is a natural number greater than 1 whose only factors are 1 and itself. So the first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. That's more like several. That's more than a few. But it's a good list to get the point across that when we see a prime number, the only thing that we can break it up as is the number times 1. 17 is only 1 times 17. 29 is only 1 times 29. 5 is only 1 times 5. A composite number is everything else. A natural number greater than 1 that is not prime. So 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, 21, 22, so on and so forth. Composite numbers will have something besides 1 in itself as a factorization. So is 16 prime or composite? Well, as soon as we can think of something other than 16 times 1, for instance, 2 times 8 or 4 times 4, we know that it's composite. 31. 31 is prime because its only factors are 1 and 31. There's nothing besides 1 times 31 that'll get us 31. C, 49. Well, 7 times 7 is 49, and that's enough to say we have a composite number. So a factorization of 16 would be 2 times 8 or 4 times 4. A factorization of 49 would be 7 times 7. A prime factorization is a factorization in which all of the factors are prime numbers, and every whole number greater than 1 has exactly 1 prime factorization. No matter how we break the composite numbers down, we're going to end up with the same factorization of prime numbers. So 30. We could make a factor tree breaking down 30 into the product of two numbers. For instance, 6 times 5. 6 can be broken down further, but 5 is prime, so 5 stays 5. 6 can be 2 times 3, or 3 times 2. And 3 and 2 are both prime, so we've reached a prime factorization. 2 times 3 times 5. I said that no matter how you break it up, you're going to end up with the same prime factorization. So what if instead of 6 times 5 for 30, you did 15 times 2? Well, the 2 would stay 2. The 15 would be 3 times 5, and there's our 2 times 3 times 5 again. So 30 can be 6 times 5. It could be 2 times 15. But when it gets broken down all the way to primes, you'll have 2 times 3 times 5 no matter what. 36. Let's do it again. We'll start with 36. We'll break it up. One way to do so is 9 times 4. We can break each of those up. 9 is 3 times 3. 4 is 2 times 2. We get 3 times 3 times 2 times 2, or 3 squared times 2 squared, or 2 squared times 3 squared. Order when we multiply doesn't matter. So order of the factors in the prime factorization doesn't matter. What if you didn't pick 9 times 4? That's okay. 36 is also 6 times 6. And 6 is 2 times 3. So 2 times 3 times 2 times 3. It's the same thing. 18 times 2. 18 times 2 would be 9 times 2 times 2, which would be 3 times 3 times 2 times 2. Same thing. No matter how you break it up, you'll get the same prime factorization. To assist with breaking numbers up, it might be helpful to know the divisibility tests, at least the ones for 2, 3, and 5. A whole number is divisible by 2 if the last digit is even. If the last digit is 0, 2, 4, 6, or 8, we can divide by 2. 2 will be a factor. A number is divisible by 3 if the sum of the digits is divisible by 3. So 144, if we add the digits 1 plus 4 plus 4, we get 9. 9 is divisible by 3, so 144 is divisible by 3. And a whole number is divisible by 5 if the last digit is 0 or 5. So 1115 is divisible by 5 because the last digit is a 5. Not listed here, but another common divisibility test is the divisibility by 10. If the number ends in 0, it's divisible by 10. Write the prime factorization of 63. We need to be able to see 63 and immediately go 9 times 7. We need to know our multiplication facts. So we can break up 63 as 9 times 7. 9 is 3 times 3. 3 times 3 times 7 would be the prime factorization. But let's say we didn't know 9 times 7. We can still use our divisibility rules to break this down. We'd start with 2. Is 63 divisible by 2? No. We'd move on to 3. Is 63 divisible by 3? Yes, because 6 plus 3 is 9, and 9 is divisible by 3. So the first prime number 2 does not divide evenly, but 3 does. We can do 63 divided by 3. That gives us 21. 21's not prime, so we do it again. Does 21 divide by 2? No. Does 21 divide by 3? Yes. 21 divided by 3 is 7. 7 is prime, so 7, 3, and 3 are our factors. 3 times 3 times 7. So we can use this division method instead of the factor tree if we need to. But we could easily have done this division in factored tree form as well. 63 is 3 times 21. 21 is 3 times 7. 3 times 3 times 7. Fractions that represent the same portion of a whole are called equivalent fractions. Earlier, when we were examining the number line, I pointed out that they referred to 2/4 as 1/2. Those would be equivalent fractions. They both represent 1/2. There are many equivalent forms of a fraction. A special form is called simplest form. And the simplest form of a fraction means that the numerator and denominator have no common factors other than 1. How do we get simplest form? We look for a number that we can multiply both the top and the bottom by.
So try to think of a number that these have in common. They're both even. So they're both divisible by 2. 10 is 2 times 5. 42, if we divide that by 2, we get 21. So we're going to cancel these 2's. It's going to leave us with 5 over 21. And 5 and 21 have no numbers in common. So 5 over 21 is simplest form. Nine 27ths. 9 and 27 have 9 in common. 9 times 1 is 9. 9 times 3 is 27. We can cancel those 9's and get 1 over 3. I want to look at this one more time, though. 9 over 27. Let's say you did 3 times 3 is 9, and 3 times 9 is 27. Then you cancel a 3 on the top and a 3 on the bottom, and you're left with 3 over 9. That can't be simplest form, though, because 3 and 9 still have something in common. 3 times 1 is 3. 3 times 3 is 9. Cancel the 3's to get us down to 1/3. So no matter how many times it takes, you're going to get to the correct answer of 1/3. C, we have 8 over 36. 8 is 4 times 2. 36 is 4 times 9. The 4's cancel, and we're left with 2/9. Another way of getting simplest form, kind of like this, but more meticulous. For instance, here, how did we know not to stop at 3/9? Well, we had to realize 3 and 9 had a factor in common. If we didn't realize that, we'd have said 3/9 was the answer and we'd have been wrong. This next method guarantees that we will get to simplest form without having to realize anything.
For larger numbers that we might not be comfortable finding a number that multiplies into both of them, we can always use the prime factorizations and divide by the common factors.
So, let's write in simplest form 50 over 22. We'll start there, because we need factor tree for 50. We need a factor tree for 22. 50 is 25 times 2. 25 is 5 times 5. So 50, and I'm going to leave this written out when we do it this way. So the top of this fraction is 2 times 5 times 5. I don't need exponential form here because I want to be able to see all of them. Also with 50, maybe 5 times 10, and then 10 would be 5 times 2. There's another way of getting 5 times 5 times 2. 22 is 2 times 11, both prime. So we see that this is now 2 times 5 times 5 over 2 times 11. The 2's cancel. 5 times 5 is left over, which is 25. 11 is left over on the bottom. 25 over 11 would be simplest form. Next up, 9 over 90. So we need a factor tree for 9. We need a factor tree for 90. 9 is 3 times 3. 90 is 9 times 10. 9 is 3 times 3. 10 is 2 times 5. So, rewriting this, 9 is 3 times 3. 90 is 2 times 3 times 3 times 5. The 3's cancel, both of them, because there's 2 on the top and 2 on the bottom. That leaves us with 2 times 5 is 10 on the bottom. And on the top, there's nothing left. But wait, we can put times 1 there, no problem, which means there's a 1 left. When everything disappears, when everything cancels away, it leaves a 1, not a 0. 1/10. Next, 35 over 75. So we need a factor tree for 35, a factor tree for 75. 35 is 5 times 7. Both prime. 75 is 3 times 25. 25 is 5 times 5. So this is 5 times 7 over 3 times 5 times 5. One 5 on the top cancels with 1 5 on the bottom. We're left with 7 on top, and 3 times 5 is 15 on the bottom. 7/15.
Oh, now we've got variables. We weren't expecting this, but we can still handle it. If it was just 7 over 56, we would do prime factorizations. Prime factorization of 7 is 7 times 1. We don't even need the prime factorization. If we know that we have a 7 that we need to get rid of, 56 makes us think 7 times 8. So we can leave it 7 times 8, so that 7 cancels and we're left with our 8, or we can take it further and do 7 times 2 times 2 times 2, but we just end up multiplying those 2's back together to get the 8. A cubed is a times a times a. A squared is a times a. The 7's cancel. A set of a's cancel. Another set of a's cancel. That leaves us with a on top and 8 on the bottom. A over 8.
Our next example asks us to determine whether 3/9 and 2/6 are equivalent. And one way to tell if two fractions are equivalent is that they would both reduce to the same fraction. If we put both of them in lowest terms, if they are the same, then they are equivalent fractions. 3 is 3 times 1, 9 is 3 times 3. The 3's cancel, 3/9 is 1/3. Or we can think of it as dividing top and bottom by 3. 3 divided by 3 is 1. 9 divided by 3 is 3. Two over 6. 2 is 2 times 1. 6 is 2 times 3. The 2's cancel. There again we have 1/3. So 3/9 and 2/6 are equivalent because they both reduce to 1/3.
We can take cross products. We can cross multiply. We do that over an equal sign. When we have fraction equals fraction, we're allowed to cross multiply. Then and only then. And if we multiply along the diagonals, for instance, here in 6/24 and 2/8, 8 times 6 is one diagonal. 24 times 2 is another diagonal. Both of those equal 48. Since the cross products are equal, that means the fractions are equal. And on the other hand, if we do that and we get two numbers that are not the same, if the cross products are not equal, then the fractions are not equal.
Determine whether 2/5 and 4/11 are equivalent by cross multiplying. Well, 2 times 11, 5 times 4 is 22, and 20, they are not equal, so no, they are not equivalent fractions. We'll finish up here with this example that I have worked out. There are 5,280 feet in a mile. What fraction of a mile is represented by 2,640? Now we can divide the top and bottom by the same number repeatedly to get to our reduced form. And here, 2,640 and 5,280, wouldn't you know, they both have a factor of 2,640, except you wouldn't know because that's a difficult number. So this shows we can just quickly divide by 2,640 to get to our answer of 1/2. I'm here to show you that we don't have to realize that. We can take it one little step at a time. So what fraction of a mile, so what fraction of the 5,280 is 2,640? First of all, they both end in 0. So let's divide both by 10. That's going to give us 264 over 528. And now they're both even. So let's divide top and bottom by 2. Now notice, I'm not dividing everything by 10. I'm dividing the top by 10 and the bottom by 10. 10 over 10 is 1. I'm dividing by 1, which means I'm not changing anything. So make sure you don't write divided by 10 without writing it in both places. So if we divide top and bottom by 2, we're going to get 132 over 264. And both of those are still even. So let's divide by 2 again. $66 over 132. And guess what? They're both even, so let's divide by 2 again. 33 and 66. And around this point you can see, hey, this is 1/2. Maybe divide both by 11 maybe, which gives us 3 over 6, and then divide both by 3. And get 1/2.
And that is it for this topic. The topic is multiplying and dividing fractions. The objectives in this topic: multiplying fractions, evaluate exponential expressions with fractional bases, divide fractions, multiply and divide given fractional replacement values, and solve applications that require multiplication of fractions. So to multiply two fractions, we multiply the numerators and multiply the denominators. This is one way that fractions work the way you would want them to work, the way you would naturally expect them to work. We just multiply across the top and multiply across the bottom. If we have A over B times C over D, that would be A times C over B times D. To remind you, if we had something like 24 over, let's keep it easy, 48. I said that you can do prime factorizations. 24 would be 2 times 2 times 2 times 3. 48 would be 2 times 2 times 2 times 2 times 3. And then we said we could cancel pairs. And we can only do this if it was all multiplication on the top, all multiplication on the bottom. There's nothing left on top, and we know because anything is itself times 1, there's really a 1 left on the top, and we're left with 1 over 2. The reason this works is because of how we're going to learn how to multiply fractions. Remember, anything over itself equals 1. So 2 over 2 equals 1. 3 over 3 equals 1. The rule for multiplying fractions is going to be that we just multiply across the top and multiply across the bottom. It's quite simple. Addition, subtraction, division, not so simple. But multiplication itself we can deal with. So really what's happening when we reduce this is we're getting 2 over 2 times 2 over 2 times 2 over 2 times 3 over 3 times 1 over 2. Whoops. Times 1 over 2. And then this becomes 1 times 1 times 1 times 1 times 1/2, which is just 1/2. So that's what's at play here. Multiplying two fractions is exactly the same as multiplying across the top and multiplying across the bottom. This is an extreme example that I wanted to use to show why simplifying works. But we can just take something like 5/6 times 1/8. Multiply across the top, 5 times 1. Multiply across the bottom, 6 times 8. 5 times 1 is 5. 6 times 8 is 48. So this one is 5/48. We had 9/7 times 1/4. Multiply across the top, 9 times 1. Multiply across the bottom, 7 times 4. 9 times 1 is 9. 7 times 4 is 28. 9/28. Another one. 3/8 times 5/2. 3 times 5 over 8 times 2. 15 over 16. Now, something's going to be a little bit different in the next one. And you might not be able to see what it is right away, but I'll point it out once we get to the answer. Multiply across the top, 3 times 4. Multiply across the bottom, 8 times 7. 3 times 4 is 12. 8 times 7 is 56. And right here, when we get 12 over 56, we notice they're both even. That's a divisibility rule for 2. Both of these share at least a factor of 2. We're going to have to reduce it. So how do we reduce? Prime factorizations will work. 12 is 2 times 2 times 3. 56 would be 2 times 2 times 2 times 7. Pair of 2's cancel, pair of 2's cancel. 3 over 2 times 7 would be 3/14. Or you can just start thinking of common factors. From 12 over 56, we know that 12 would be 2 times 6. 56 is 2 times something. How do we find out what that is? We divide. 56 divided by 2. 2 goes into 5 twice. 2 goes into 16 8 times. It'd be 2 times 28. That pair of 2's cancels. We're left with 6 over 28, but 6 is 2 times 3. 28 is 2 times 14. The pair of 2's cancel, and there's our 3 over 14. I'm going to show you an easier way than just multiplying across and multiplying across the top and multiplying across the bottom.
This is called canceling. And it's called canceling because we start canceling common factors from the very beginning before we take that step of multiplying. How do we know when we can cancel? Well, 3/8 can't be reduced. 4/7 can't be reduced. But we should also look at anything from the top with anything from the bottom. And 4/8, that would be able to be reduced. 4/8 is 1/2. So what we're going to do is look for numbers on the top and on the bottom that both can be divided by the same number, and then we do it. 4 and 8 can both be divided by 4. 4 divided by 4 is 1. 8 divided by 4 is 2. And then those new numbers become what we have in those parts of the fraction. So really, this would be 3 times 1 over 2 times 7. 3 times 1 is 3. 2 times 7 is 14. When we cancel completely, we're not going to need to reduce. We got rid of all the common factors up front. What if you didn't notice that they're both divisible by 4? What if you just notice that they're both divisible by 2? That's okay. 4 divided by 2 is 2. 8 divided by 2 is 4. We just run our checks for cancellation again. Is there anything from the top that has a factor shared with something in the bottom? And yeah, 2 and 4, they can both be divided by 2 again. 2 divided by 2 is 1. 4 divided by 2 is 2. 3 times 1 is 3. 2 times 7 is 14. What if we canceled to get the 2 and the 4, but we didn't notice we can go further? Well, then we would end up with 3 times 2 over 4 times 7, which would be 6 over 28. And because we didn't cancel completely, we're still left with something that needs to be reduced. So you would still need to get it to 3/14. Let's look at another. Let's take a look at 15/5 times 6/5. Well, this is a problem that illustrates that canceling is very useful. Otherwise, we would have to do 15 times 6. We would have to do 5 times 5. We get 90 over 25, and we would have to reduce that. They both are divisible by 5. 5 times what is 90? 90 divided by 5. 5 goes into 9 once. 5 goes into 48 times. So it's 5 times 18 over 5 times 5. We get 18/5. And we can leave it in this form, even though it's an improper fraction. Why? Well, our rule is going to be if there's an improper fraction in the answer, you can leave it an improper fraction. Or sorry, if there's an improper fraction in the question, you can leave it improper in the answer. On the other hand, as we are going to see in the future, if there is a mixed number given in the problem, you have no choice. You have to put your answer in mixed number form if it turns out improper. but no mixed number here. We can just leave it 18/5. But there's got to be an easier way. I said canceling could work here, and then we wouldn't have to go through these big numbers. How would that work? And I am going to use cancellation where I can moving forward. 15 and 5 can both be divided by 5, whether we do this 15 and 5 or that 5. It doesn't matter which one. We need to do one of them. 15 divided by 5 is 3. Divided by 5 is 3. 5 divided by 5 is 1. Don't do both, though. One or the other. One of those 5s has to stay a 5 because 3 times 6 over 5 times 1, or 1 times 5, depending, is what gets us to our 18/5. As if DJ Khaled was here with us. Another one. 8 over 27 times 3 over 16. 8/27 can't be reduced. 3/16 can't be reduced. But 8 and 16 share some factors. 8 and 16 can both be divided by 8. 8 divided by 8 is 1. 16 divided by 8 is 2. 3 and 27 share some factors. One in particular, 3. 3 can be divided by 3. 3 divided by 3 is 1. 27 can be divided by 3. 27 divided by 3 is 9. You can see now why multiplication and division facts are very important. You need to know your multiplication tables. Make flashcards. There are websites that'll give you like flashcard games with the multiplication facts. We get 1 times 1 over 9 times 2. 1 times 1 is 1. 9 times 2 is 18. 1/18. If you don't cancel here, you would have to do 8 times 3 is 24. 27 times 16 is whatever that is, big number. And then you would have to reduce it all the way down to 1/18 to get the correct answer. The good news is, just because we're using fractions doesn't mean our 0 and 1 rules stop being what they were with whole numbers. So if we had 0 times 3/4, it doesn't matter that it's a fraction. 0 times anything is still 0. So don't let zeros fool you. Anything times 0 is still 0. 1/3 times 1/4. Is there anything to cancel here? Nope. On the top, 1 times 1. On the bottom, 3 times 4. Our answer is 1/12. From something with nice small numbers, unfortunately, to an example with very, very large numbers. 35 over 99 times 27 over 50. Now, again, here, you could do 35 times 27 is really big number. 99 times 50 is even bigger number. And then you would be responsible for reducing it all the way down to our correct answer. Or you can start looking for things to cancel. 35 over 99 doesn't reduce. 27 over 50 doesn't reduce. But 35 on the top and 50 on the bottom, as long as we can find one on the top and one on the bottom, we can cancel. They are both divisible by 5. 35 divided by 5 is 7. 50 divided by 5 is 10. We keep going. 27 and 99 are both divisible by 3, but they're also easier, both divisible by 9. 27 divided by 9 is 3. 99 divided by 9 is 11. 7 times 3 over 11 times 10 gives us our final answer of 21 over 110. We got there relatively quickly with canceling. Otherwise, 35 times 27, 99 times 50, reduce, reduce, reduce until you get 21 over 110. What about if we had 3 fractions? Let's say we have 7/6 times 1/5 times 3/35. Well, we could go all the way across the top, 7 times 1 times 3, all the way across the bottom, 6 times 5 times 35. We would like to avoid that if we can. Those numbers would be very large and we would be responsible for reducing that fraction. So we look for anything on the top that shares a factor with anything on the bottom. I see a 7 on top. I see a 35 on the bottom. Why do I know that those are both divisible by 7? Because I know my multiplication tables. 7 divided by 7 is 1. 35 divided by 7 is 5. Anything else? The 3 on the top with the 6 on the bottom. 3 divided by 3 is 1. 6 divided by 3 is 2. And now we have 1 times 1 times 1 on the top. 2 times 5 times 5 on the bottom. 1 times 1 is 1 times 1 is 1. The bottom, 2 times 5 is 10 times 5 is 50. And this one would be 1/50th. Let's do another like this. 3 fractions. One-fifth times 7 halves times 1/3. Well, nothing cancels. The only thing of interest on the top is a 7, and nothing on the bottom can be divided by 7. So we have to go straight across the top. 1 times 7 times 1. Straight across the bottom. 5 times 2 times 3. If we can't cancel, we can't cancel. Got to do it. Anything times 1 is itself. The top is just 7. On the bottom, 5 times 2 is 10 times 3 is 30. 7/30. Next. Ooh, big numbers, scary numbers. 19 over 24 times 0 times 3 over 26. There's a 3 on the top and a 24 on the bottom we can cancel. But what else do we notice? It's all multiplication, and one of the factors is 0. Anything times 0 is 0. So this one is quite simply just 0. 7/9 times 4/25. Oh my. Times 5/21. Oh my. Times 3/4. We have 4 fractions we're multiplying together here. Let's cancel what we can. Otherwise, we'd have to do 7 times 4 is 28, times 5 is 140, times 3 is 420, I believe. All over 9 times 25 is 225, times 4 would be 900, times 21 would be big number. So big number over big number, we would have to reduce that. So we would like to cancel. I like seeing this 4 on the top and this 4 on the bottom. That's a pair. It reduces to 1 over 1. 7 over 21, that's 1/3. 7 divided by 7 is 1. 21 divided by 7 is 3. Hey, there's a 3 on the top that can go with that 3 on the bottom. 1 and 1. 5 on the top, 25 on the bottom, that's 1/5. 5 divided by 5 is 1. 25 divided by 5 is 5. So all of that just to get all ones on the top. 1 times 1 times 1 times 1. And on the bottom, we have 9 times 5 times 1 times 1. So we get an answer of 1 over 45. So those huge numbers we would have gotten if we just multiplied across and multiplied across the bottom. We would have had to reduce that all the way down to 1 over 45. Cancellation was very helpful here. I also want to point out, what if instead of that 3 with the new 3, what if instead, before we even got there, we did this 3 with this 9? 3/9 is 1/3. Well, we still get all ones on the top, and now on the bottom, 3 times 5 times 3, 3 times 3 gives us that 9. So no matter what order we cancel and which numbers we cancel with, as long as we're doing correct things, the only thing we can come up with is the correct answer. If you get anything else, either it's not reduced completely and it reduces to the correct answer, or you've done something wrong and you don't have the right answer.